Hey everyone, this is Bhargav Sudhar, and today we will learn about what is a permutation group. So in this today's session, we will discuss about some properties of a group and also permutation group and some examples. Okay. So first, let us discuss what are the properties of a group. In previous session, we discussed what is a group and what are the conditions to become a group. Okay. So the first one, identity element. So whatever the identity element we are getting, that is unique. The second property is inverse element is unique. Fine. And the third one, if inverse of A is B, then the inverse of B is A. Okay. So these are the properties of a group. Fine. Now, let us discuss what is a permutation. So suppose S is a non-empty finite set having n distinct elements. Okay. Then a 1-1 on 2 function. Now we all know what is a 1-1 on 2 function, and in case you don't know, just go to the function video. Okay, so then a 1-1 on 2 function from S to S is called a permutation of degree n. Fine. Now note. So see, there exist n factorial distinct permutations from the set S to the set itself, or to the set S. And the set of all permutations is known as permutation set, and it is denoted by the symbol P subscript n. Right? Now let us jump to permutation group. So what is a permutation group? If Pn is the set of permutations and composition function is a composition defined on the set S, then Pm forms a group and is known as a permutation group. Okay, and we know what is a group. So composition function, it is a composition defined on the S, then this Pn forms a group and is known as a permutation group. What are the notations for the permutation? See, if we have the set S is x1, x2 up to xn, and sigma, let us denote sigma as a permutation, then what? So then this is the symbol sigma equals to this brackets. Now write x1 and then sigma x1, x2 sigma x2, x3 sigma x3 up to xn sigma xn. So that means we have the set from x1 to xn, and sigma of x1, that means permutation of x1 or image of x1, then permutation of x2, permutation of x3 up to sigma of xn. So this is how you can write. We will discuss an example. Now, what is a composition? We discussed. So what is a composition? So let us take two permutations, that is f equals to a1 b1 a2 b2 up to an bn, and g as b1 c1 b2 c2 up to bn cn. Then the composition, the fg, it is denoted by this symbol, that is a1 c1 a2 c2 up to an cn. How? See, as you can see that a1, and this is sigma of a1, so that is the image is b1, so that means a1 goes to b1. Now for g, b1 goes to where? So here, as you can see that this a1 goes to b1, and in g, b1 goes to c1. So the final image will be c1. So that is why we have written here a1 c1. Now a2 b2. Now a2 goes to b2, then b2 goes to what? c2. So final image will be a2 c2, and so on, and last an cn. So an goes to bn and bn goes to cn. So an and c. So this is how you can find composition. Okay. So let us discuss what is the identity permutation. So see, if every element of the set maps to itself, then it is known as the identity permutation. What are the cycle notations? So see, this is cycle notation 1 1 2 2 and n. So 1 goes to 1, 2 goes to 2, and n goes to n. Okay. Now see, suppose we have this 1 1 2 3 3 2. Okay. So how to write it in cycle notation? So as you can see that this 1 goes to 1, so that is only one cycle. Now 2 goes to 3 and 3 goes to 2. So it is a cycle having two elements because they are related. So 2 goes to 3, 3 goes to 2. So the final answer will be a cycle having this only 2, 3. Why we are not writing 1? Because 1 is 1 goes to 1 itself. So if we don't write, that means it is very obvious, right? Suppose we have this example. Now 1 4 2 2 3 7 4 5 5 1 6 6 7 3. So how to write it? So first step. Now see, 1 goes to 4. Now 4 goes to 5. Then 5 goes to 1. Okay. So 1 to 1. So one cycle is completed. Now in cycle, 1 goes to 4, 4 goes to 5 and 5 goes to 1. So we are writing this. Now 2 goes to 2. So we are simply writing this 2. Fine. Now 3 goes to 7 and 7 goes to 3. So one cycle is completed. So 3, 7. And last 6 goes to 6. So a cycle having one element. But the final answer will be what? This 1, 4, 5 cycle and 3, 7. So that means this 2, if we don't write 2 and 6, then it is automatically, or it is very obvious that 2 is 2 goes to 2 and 6 goes to 6. Okay. Now let us discuss example. So let S equals to 1, 2, 3, and then P3, it is set of all distinct 1, 1, 1, 2 functions from S to itself. That is, this P3 is what? Set of all F, such that F is a permutation of degree 3. Now show that P3 is a permutation group with respect to the composition of function. So we need to find whether it is a group, whether it is a permutation group, and the operation is what? Composition of function. Okay. Now see, solution. So as you can see that the degree is what? 3. So by that theorem or note, it will contain how many elements? That is 3 factor. So that is 6. So hence there will be 6 distinct permutations. Okay. And what are they? So P3 equals to what? See, this is the identity permutation 1, 1, 2, 2, 3, 3. Okay. And we know the permutations. So we can write this rest of the 3. Like 1, 1, 2, 3, 3, 2, 1, 2, 2, 1, 3, 3, 1, 2, 2, 3, 3, 1, 1, 3, 2, 1, 3, 2, and 1, 3, 2, 2, 3, 1. Okay. Now see, let us denote this. So let I equals to this one. Let then F1 equals to second one, F2, then this is F3, this is F4, and this is F5. Right? So the composite of functions is defined as operation of P3. So let us discuss that. See how to write this F1 and F2, F1 composition F2. Let us first discuss, see, we need to create this type of table, right, as we did in previous lectures. So this is the composition. We have total 6 elements. So I, F1, F2, F3, F4, F5, and in same way row I, F1, F2, F3, F4, and F5. Now how to write this? So I composition I, that will obvious. Now let us discuss this. See, F1 and F2. So consider this. Where is F1? F1 and F2. So how to write it? See, 1 goes to 1, and here in F2, 1 goes to 2. So the final answer will be here 1, 2, right? Now 2 goes to 3, and in F2, 3 goes to 3, so 2, 3. So here it will be 2, 3. Now 3 goes to 2, and 2 goes to 1. So final answer will be 3, 1. And this, whatever the new permutation we've got, that is already there. That is F3. So F1 and F2 equals to F3. So answer of F1, F2, it will be F3. So as you can see that this F1 composition F2, that is F3. So in same manner, you can calculate each and every terms. So now we need to find what? We need to check it is a group. Okay. So for group, closure is there. As you can see that this all the elements, they are from what? They are from this given set, that is I, F1, F2, F3, F4. They all are I, F1, F2, F3, and F4. Okay. Now the second one, associative. You can check it at your own that it is associative. Then the third property is what? Existence of identity. Now for identity element, what we need to check? So that means some element into the element that will get itself. So that means element into or element composition, the identity element, then we'll get the element itself. So just by table, what is this identity element? So that is I. As you can see that this I into I, we are getting I. Now F1, then F1 into I, so we are getting itself. F1, now F2 into I, so we are getting F2. So that means I, it is the identity element and it is the unique one. Okay. Then the existence of inverse. Now for inverse, what we need to find? The element in then composition, the inverse element. Then we are getting I. So that means just consider this. Now I into I, that is I. So that means for I is the inverse. Now for F1, where is I? So I. So that means if we compose it F1 and F1, then we are getting I. So that means what? F1's inverse is F1. Now for F2, so F2 into F2 we are getting I. So that means F2's inverse is F2. in same manner F3's inverse is what? Here F3's inverse is F4, F4's inverse is F3, and F5's inverse is F5. So inverse is there, right? And yes, that's it. So it is a group. So hence it is a group. So this is how you can find whether it is a permutation group or not. Thank you.